In this video, I am going to explain a new chapter on dynamic programming. Introduction. Dynamic programming is a mathematical technique which deals with the optimization of multi-stage decision problem. So in dynamic programming, the problem is divided into number of stages and each stage is optimized individually, and further by integrating all that substages or stages, the solution or the problem is optimized. This technique was developed by Richard Bellman and G.B. Dancing in 1950. Dynamic programming differs from linear programming problems in two ways. In dynamic programming, a standard mathematical formulation does not exist. Particular equation must be developed to fit for each individual situation. So we have seen in linear programming problems that there is a standard mathematical formulation for every LPP by using which the objective function is optimized, but that type of standard formulation does not exist in dynamic programming. Every individual problem have a particular equation which must be developed to fit for each individual situation. Linear programming gives one-time solution, that is single stage solution, whereas dynamic programming considers decision making over time and solves each sub-problems optimally. Dynamic programming is a technique for solving problems in which decisions have to be made at each successive stages. It provides a systematic procedure for determining the combination of decisions that maximizes overall effectiveness. So as I told, in dynamic programming, the problem is divided into number of sub-problems that are called stages, and each stage is solved for the optimization. In dynamic programming, the problem is divided into number of sub-problems or stages, and the solution of sub-problems are then combined to get overall solution. Next point is terminology used in dynamic programming. The first term used in dynamic programming is stage. The dynamic programming problem is broken into sub-problems and each sub-problem is called stage. Second term is stage decision. At each stage, there are number of alternatives and the selection of one of the most suitable and feasible alternative is called stage decision. Next term is state variables. The variables whose values specify the condition of the decision process and summarize the current status of the system are called state variables. Next term is decision variables. The unknown in the given problem that need to be determined are called decision variables. Next term is a return function. At each stage, a decision is made which can affect the state of the system. at the next stage. It can be described in an algebraic equation form. The equation which represents the contribution of each stage is called a return function. Next term is recursive relationship. Recursive relationship represents a mathematical expression connecting the optimal solution of the earlier stage and the return function from the current stage. The next important point is Bellman principle. The statement of this principle is an optimal policy has the property that whatever be the initial stage and initial decision, the remaining decisions must constitute an optimal policy for the state resulting from the first decision. So this implies that whatever may be your initial decision or decision in the intermediate stages, you can optimize that decision in the further stages. Now we will see the dynamic programming algorithm. What are the various stages by following which the dynamic programming problem is solved? The first stage is identify the decision variables and specify objective function to be optimized under certain limitations, if any. Stage 2, divide the given problem into number of stages. Identify stage 3 or third step is identify the state variables at each stage and write down the transformation function as a function of state variable and a decision variable at the next stage. Step number 4, write down the general recursive relationship for computing the optimal policy. Step number 5, decide whether forward or backward method is to follow to solve the problem. Step number 6, construct appropriate stages to show a required value of the return function at each stage. Step number 7, determine the overall optimal policy or decisions and its value at each stage. Now in the step number 5, it is given that we have to decide forward or backward method of computation. So what is forward and backward method of computation? So forward and backward computational procedure. First one is forward computational procedure. When the dynamic programming problem is solved using the recursive equation starting from the first stage to the last stage, the computation involved is called the forward computational procedure. When the dynamic programming problem is solved using the recursive equation starting from the last stage to the first stage, the computation involved is called the backward computational procedure. Now let's take one example and understand how the dynamic programming problems are solved using forward or backward computational procedure. Now this is the problem of shortest path, or it is also called stagecoach problem. The problem is a sales manager is planning a business tour from Mumbai to Kolkata. He intends to cover one town from each of the company's different marketing zones on the route The network shows the three intermediate stages and three possible choices of the route at all but the last cities. The travel time between the two cities inclusive of working time is given below, and the arrows between cities. Which intermediate cities should he visit to minimize the time required to go from A to H? So in this given problem, the city A is nothing but the Mumbai and city H is nothing but the H. These are the various zones through which the salesman these are the various zones, or these are the various cities through which the sales manager have to pass to go to city H. Now this circled figures shows the time required to go from one city to another city. For example, this 5 number shows 5 unit time to go from city A to city B. Now in this problem we have to select, or the sales manager have to select the shortest path by following which he can go from city A to city H. So he had present many options that he can go from A to B, B to E, E to H, or A to B, B to F, F to H, so like that. So amongst all the possible paths, the sales manager has to select the shortest path. So this selection of shortest path can be made with the help of dynamic program. Now, as I told earlier, in the dynamic programming problem, the problem is divided into number of stages. So this dynamic programming problem, we will divide this problem into 3 number of stages. So this will be the stage number 1, this will be stage number 2, so this will be the stage number 1, this will be stage number 2, and this one stage number 3. Okay. So stage 1, now we have started from right and we are going towards left. So that means the computational procedure we are going to use is backward computational procedure. So stage 1 represents the stage or the optimization of time when the salesman goes from E to H or F to H or G to H. Stage 2 represents optimization when the salesman have to go from B to E, F or G, or C to E, F or G, or D to these 3 cities. And like that, stage 3 represents the optimization when the sales manager have to go from A to either B, C or D. Now let us optimize the stage 1. Now in the stage 1, there is only one alternative, that wherever may be the position of the sales manager, that is wherever may be the sales manager, that is either city E or F or G, he has only one alternative to go from this city. That alternative is H. The possible state variables are city E, F or G, or node E, F or G. The recursive function, it is F1 of x1 is equal to D1 of x1 M1. So this recursive function I will explain latter. Now in this table, first column represents the state variables x1. The state variables are E, F and G. The second column represents the various alternatives. So there is only one alternative, that is H. F1 of x1 star represents the stage decision. So amongst this state variable and alternative, this combination, the best decision the sales manager have to take, and this will be written in this column. So the possible state variables are E, F and G. There is only one alternative, that is H. Now when the salesman want to travel from A to H, 3 units of time is required. So this will be represented in this cell. When the salesman want to travel from F to H, the time or before that, the stage decision is 3 units. So there is only one option which is available with the sales manager, and this one is this alternative, and this one is this time. So F1 of x1 star value is 3 with respect to alternative H. Now the salesman want to travel from F to H, so at that time he require the time 4 units. So in that case, the value of F1 of x1 star will be 4 with respect to the alternative H. Similarly, the salesman want to travel from city G to H, so at that time the time required is 3 units. So the value of F1 of x1 star is 3 with respect to alternative H. So this value represents the stage decision. Now if we see this table, there is only one alternative. So the salesman is not having any option. So that's why whatever may be the value in this column, it will be the value of F1 of x1 star, and the alternative will remain same in every cell of the column 3, that is H. Now let's move towards the stage 2, that is the salesman is at the position B, C or D, and he want to travel from these locations to either E, F or G. Now stage 2, this table shows the output from the stage 1. So with respect to state variables E, F and G, the values of decision variables, state decisions are 3, 4 and 3. Now in the stage 2, the possible alternatives are E, F and G. The possible state variables are B, C and D. So salesman can travel from B to either E, F or G, or from C to either E, F or G, or from D to either E, F or G. Now the recursive function for this stage is F2 of x2 equal to D of x2 plus F1 of x1. Now the various state variables are B, C and D. Now here 3 alternatives are there, E, F and G. Now salesman, let us assume that the salesman is at the position B and he want to travel from B to E. So as per the recursive function, the value will be d of x2, that will be the value of this 5. So when the salesman want to travel from B to A, the 5 unit time will be required. So that is a d of x2 plus 3 unit of time required to go from E to H. So when salesman want to travel from B to H via E, the time required is 5 plus 3. So 5, it is d of x2 plus f1 of x1, it is 3. It is represented here. So E to H time required is 3. So this one, f1 of x1. So this is 5 plus 3 equal to 8. Now let us, now by assuming that the salesman is at the city B and he want to travel from B to H via F. So the time required will be d of x2 will be 7 unit plus f1 of x1. For f it is 4. So 7 plus 4, it is 11. Similarly, the salesman want to travel from B to H via G. The time required will be d of x2, that is 7 unit plus f1 of x1 for the city G, it is 3. So 7 plus 3, it is 10. Now amongst these three values, the best value is that is minimum value is 8 unit. So that is the stage decision. So f2 of x2 star value will be 8 with respect to alternative E. Similarly, the salesman is at the state C and he want to travel to city H via E. The time required will be C to E is 6 plus f1 of x1 for the E will be 3. So 6 plus 3, it is 9. From C to F or C, F, H, the time required will be C to F, it is 7 and F to H, it is 4, or f1 of x1 for F, it is 4. So it is 7 plus 4, 11. Similarly, from C to G is 10 plus 3. So d of x2 is 10 plus f1 of x1 for G, it is 3. So 10 plus 3, it is 13. So amongst these three values, the minimum is 9 with respect to alternative E. So this will be our stage decision. So 9 with respect to alternative E. Similarly, DEH, traveling for the DEH, the time required will be 6 plus 3 equal to 9. DE, time required is 6. E to H is 3, so 6 plus 3, it is 9. D to F, F to H, the time required is D to F, it is 8. F to H, it is 4. So 8 plus 4, it is 12. D to G and G to H, the time required is D to G, it is 9 plus G to H, it is 3. So 9 plus 3, it is 12. The minimum value among these value is 9 with respect to alternative E. So this is our stage decision with respect to alternative E. So in this way the stage 2 is completed. Now let's move towards the stage 3. Now in the stage 3, the possible alternatives are B, C and D. The possible state variable is only one, that is A. So salesman can travel from city A either to B or C or D. the recursive function is f3 of x3 equal to d of x3. This value will be the values of d of x3 5 5 3 plus f2 of x2. Now the state variable is only a. The possible alternatives are B, C and D. Now the salesman want to travel from A to B and B to H. So the time required will be A to B 5. So D of x3 will be 5 plus f2 of x2. For B it is 8. So it will be 5 plus 8 13. Similarly, the salesman want to travel from, or sales manager want to travel from A to C and C to H. With the help of recursive function, the time required is d of x3, it is 5 plus f2 of x2 for the C is 9. So 5 plus 9 it is 14. Similarly, A to D and D to H, the time required is A to D it is 3 plus, with the help of recursive function, f2 of x2 for D is 9. So 3 plus 9 it is 12. So amongst these three values 5, 13, 14 and 12, 12 is the minimum, which is called stage decision with respect to alternative D. So in this way the stage 3 is completed. Now let's integrate all the three stages. This one is stage 1, this one is stage 2 and this one is stage 3. Now with the help of these three stages, the shortest path is determined like this. In the stage 3, the salesman can travel from the stage 3 we can determine that the salesman have to travel from A to D. With the help of stage 2 we can say that salesman has to travel from D to E, and with the help of stage 1 we can say that the salesman has to travel from E to H. So when this path is followed by the salesman or sales manager, this path will be the shortest path with distance or time so if this path is followed by the sales manager, that is A to D and D to E, E to H, the shortest time will be obtained, and that time is 12 units. So A to D, D to E and E to H. So by following this path, if he follow this path will be the shortest path with time 12 units. Thank you.